Everyone. My name is L. Sriram Kumar. I'm a cosmologist working at the Department of Physics here at IIT Madras. Welcome to the second lecture of the Subra Suresh Distinguished Lecture Series, which will be given by the Nobel laureate, Professor Brian Schmidt. Professor Schmidt, it's indeed a pleasure and privilege to have you with us. I'll now request everyone to stand up for the Tamil Thai Varthu, the state anthem of Tamil Nadu.
நீராறும் கடலுடுத்த நிலமடந்தை கெழிலொழுகும் சீராறும் வதனமென திகழ்பரத கண்டமிதில் தெக்கணமும் மதில் சிறந்த திராவிடனல் திருநாடும் தக்க சிறு பிறை நுதலும் தரிதனரும் திலகமுமே அத்திலக வாசனை போல் அனைத்துலகும் இன்பமுற எத்திசையும் புகழ் மணக்க இருந்த பெரும் தமிழனங்கே தமிழனங்கே உன் சீரிழமை திறம் வியந்து செயல் மறந்து வாழ்த்துதுமே வாழ்த்துதுமே வாழ்த்துதுமே.
Please be seated. Dear students and colleagues, as I said, Professor Schmidt's lecture today will be the second lecture of the Subra Suresh Distinguished Lecture Series. Let me welcome you all once again to the lecture. I'd like to mention that apart from Professor Schmidt, we have a few distinguished guests with us today. We have with us Professor Subra Suresh, our distinguished alumni, former director of the National Science Foundation, USA, and the current president of the Nanyang Technological University, Singapore, who has lent his name to the lecture series and who has joined us online. And we also have with us Mr. Senapati Kris Gopalakrishnan, co-founder of Infosys, and our distinguished alumni who has provided support to the lecture series. And of course, we have our deans, Professor Mahesh Panchagnula, Dean for Alumni and Corporate Relations, and Professor Raghunathan Rangaswamy, Dean for Global Engagement, who have facilitated the lecture series and the organization of the lectures. I will now request Professor Mahesh Panchagnula, our Dean for Alumni and Corporate Relations, to say a few words of introduction about the new lecture series. Mahesh.
Thank you, Sriram. Good evening and welcome to this lecture today by Professor Brian Schmidt, the Subra Suresh Distinguished Lecture Series in its second edition. We had Professor Didier Queloz give the first inaugural talk a few months ago. And it's a delight to have Brian here from Australian National University, a leading luminary in the field of astronomy and cosmology, but also a vice chancellor of the topmost, the best university in Australia. That's a rare combination that I've found. So thank you very much for making the time from your busy schedule to be here with us. Also, I want to acknowledge with gratitude the support of Kris, who has made this and many, many other path-breaking initiatives at IIT Madras happen for all of us. He's been a well-wisher of IIT Madras in every definition of the word, and incidentally a physics graduate as well. So physics department should be doubly proud of the fact that a physics alumnus has come back and done this for the department. I also want to thank Professor Subra Suresh, who was, as Sriram mentioned, the former director of the National Science Foundation, the bedrock on which for many decades US research has been built, as well as until recently the president of the Nanyang Tech University, where under his leadership, the university grew from what was a very good Singapore university to one that's reckoned on the global stage today. So, and he has also been a well-wisher of IIT Madras in many ways. And thanks to his efforts, we've been able to bring speakers like Didier and Brian to our campus. We are grateful to you, Subra, for having lent your name and for having ideated this lecture series along with Kris. Lastly, I want to talk about IIT Madras of today. IIT Madras of today is a very aspirational institution. We are, by every definition of the word, among the best in India. And some rankings say we've been there for a long time. We've been the best for a long time. But we are certainly not content and not happy with where we are. We want to be reckoned on the global stage as being a positively contributing, impactful university by every definition of the word. And the beauty of this aspiration is that words that are used as adjectives in this sentence can be defined by each and every one of us to suit our frame of mind. And that's the freedom that IIT Madras provides each and every one of us. And that's the freedom that we so cherish and wish to strengthen as we grow in this direction of being a more impactful, globally relevant university. Lecture series such as this help that aspiration to a great extent. Thank you very much, all of you, for coming, and I look forward to the lecture.
Thank you, Mahesh. I will now request Professor Raghunathan Rangaswamy, our Dean for Global Engagement, to say a few words.
Thank you, Kris, Subra, and Prof. Brian for being here. I'll keep my remarks very brief. I said this yesterday also. When I look at the IIT of today, and just the month of December, as I keep mentioning, we had about 15 international conferences in the campus. And I've been in many universities. I've never seen that happen in a university campus. So a place is actually measured by the kind of intellectual discourse that takes place. And all of these international conferences and seminars and workshops really build an intellectual discourse that all of you should participate in. And I mentioned this yesterday too. I was an undergrad here. I would have given anything to be sitting in so many good lectures during my undergraduate. I probably sat through maybe one. I can't recall, but I would have given anything to be here at this time as a student. And we do many of this for our students, and I hope all of you benefit from this tremendously and learn and aspire to be giving such lectures in the future. Thank you again for coming in big numbers, and I hope you have a great time here listening to this wonderful lecture. Thank you.
Thank you, Raghu. I will now invite Professor Subra Suresh, our distinguished alumni, former director of the National Science Foundation USA, and the current president of the Nanyang Technical University, Singapore, to address this audience.
Thank you very much.
Yes. Apologies. My apologies. Professor Subra Suresh, over to you.
Thank you very much. Good afternoon, everyone. First of all, my apologies for not being able to participate in person. Let me, first of all, express my profound gratitude to Professor Brian Schmidt, a friend and a colleague that I've known for some time. And I warmly welcome him to IIT Madras on behalf of all of you. Also, let me thank Kris Gopalakrishnan and also IIT Madras for launching this lecture series. I'll be extremely brief as well. I just want to make one comment about what we just heard about aspirations for IIT Madras. In its relatively short existence of only about 60 years or so, IIT Madras has had a tremendous impact both within India and outside India through the cumulative accomplishments of many of its alumni and the intellectual atmosphere that has created both through its education and also the impact of the alumni. I think moving forward, one of the other ways in which significant further impact can be achieved is through accomplishments in generating new knowledge through research and through the impact of that research on innovation, entrepreneurship, and many other areas. In that respect, I think lectures such as this will provide an opportunity to inspire and motivate students. So I hope that full advantage is taken of such an opportunity by students. And again, I want to thank the Institute for facilitating this lecture. Thank you.
Thank you, Professor Subra Suresh. I will now request Mr. Kris Gopalakrishnan, co-founder of Infosys and our distinguished alumni, to address this one.
Thank you very much, and thank you, Subra. It's probably very early morning for Subra, and thank you for taking time. And it shows also his commitment to this lecture series, commitment to IIT Madras, and of course his respect for Brian, that he woke up so early to attend this. I also want to start by thanking Professor Brian Schmidt. It's an honor and privilege for us to host you here, and we really thank you for spending time with us. Not just the lecture, but the 2 days that you spent in the campus, meeting various faculty, students, and looking at ways in which we can collaborate. The purpose behind these lectures, of course, is sharing knowledge, but also creating that excitement in world-class research, world-class science, what is possible today. And I feel that we are living in exciting times. Technology progress that we have made hitherto, I think combining together in a multidisciplinary manner, creating opportunities to do more exciting things. And I feel that several breakthroughs in multiple fields are going to happen simultaneously over the next few years. So, to the students here, I think sky is the limit, and literally, of course, Brian will talk about the limits actually, but sky is truly the limit. And I'm happy to see all of you here. Thank you very much for participating. The whole purpose of people, introducing people like Professor Brian Smith, Professor Subra Suresh, etc., is to say that people who have passed out from IIT Madras have gone on to do things at the top of the research ecosystem around the world. And I hope that they inspire you to think big, do brilliant things in the future. So thank you very much.
Thank you, Mr. Gopalakrishnan. We now come to the main program of today. That's the second Subra Suresh lecture by Professor Brian Schmidt. Before I hand over the stage to Professor Schmidt, I would like to briefly introduce our speaker. Professor Schmidt, as was mentioned earlier, is presently the Vice Chancellor of the Australian National University located in Canberra. He graduated with a BS in Physics and Astronomy from the University of Arizona in 1989. He received his Master of Arts in Astronomy in 1992 and then PhD in Astronomy in 1993 from Harvard University. Professor Schmidt's PhD thesis was supervised by Professor Robert Krishna, who, by the way, is also in India, visiting India today as we speak. And the thesis was aimed at observationally measuring the so-called Hubble constant, of which you will hear later today, I believe. Professor Schmidt was a postdoctoral research fellow at the Harvard and Smithsonian Center for Astrophysics during 1993-94, before moving on to the Australian National University's Mount Stromlo Observatory in 1995. He commenced his tenure as the Vice Chancellor of the Australian National University on January 1, 2016. Professor Schmidt is well known for his work towards understanding the astrophysics of exploding stars, known as supernovae. He was one of the first to recognize that a certain type of supernovae, known as type 2 supernovae, can play the role of what are known as standard candles. This property allowed us to determine the distances to faraway galaxies, which in turn led to the discovery that the universe is presently going through an accelerated expansion. For the role he had played in this discovery, along with Professor Saul Perlmutter and Professor Adam Rice, Professor Schmidt had won the 2011 Nobel Prize in Physics. I will now request Professor Schmidt to give the Subra Suresh lecture title, 3 Big Questions for Astronomy. Professor Schmidt.
All right. Great to see everyone, and it is great to be back here in Chennai. So I was last here in of May of 2017, and I guess this trip has just highlighted to me how much things have changed and changed for the better over the last 6 years, or just a little less than that. So I like to thank Subra, again, someone I've known since his time at the NSF. Kris for helping bring me back. Of course, I probably would have intended to be back a few years ago, but COVID has interceded. But IIT Madras has had a history of, certainly in my lifetime, of absolutely producing the best graduates of India. And what I'm loving to see is that continuing, but now the research programs here on campus contributing to the global knowledge in a way that the best universities do. So the rate of change here is truly astronomical, and I do know what astronomical change looks like. So congratulations. So today I'm going to talk a bit, a related lecture to what I did yesterday, but it's more forward-looking, and it's 3 big questions for astronomy. Now, I did not know when I wrote this talk that DJ had just been here. So part of it is going to overlap with DJ's talk, and so he's the expert there. So you're going to have to grade me how I do, but I'm thinking as a cosmologist, I guess, of some of these questions. So the questions I want to talk about, we'll get to in a second, but I want to step back, and I want to think about astronomy as a human pursuit. So this is the Pleiades, the 7 sisters, as it's known around the world. It's about an 80 million year old collection we call an open cluster of stars formed together. And what's really interesting about these is 80 million years they've been around. It is located at the celestial equator. So I grew up in Alaska, very far north. You can see the Pleiades. If you go to the tip of Patagonia, this further bit, you can see the Pleiades. They've been around 80 million years. Every person ever alive has seen the Pleiades. And what is remarkable are there are stories around the Pleiades around the globe. And it is described as the 7 sisters, but interestingly enough, if you go and look with really good eyes, you can only see 6 stars. And yet everywhere it's 7 sisters, or related things, 7 chicks, there's some other versions of it. Whether or not you're in South America, you're in Africa, you're in Australia, you're in this part of the world, or you're in Europe. So the same story has evolved, and I think the best guess is it is a story that we connect us all to literally 50 or 100,000 years ago, when we really were all the same people. And just to give you a sense of this, I want to show you this picture. This is the cave of Laskome. So it's 17,300 years old. And you see a bull. This is quite a famous thing. And I want you to look right there. Well, guess what? 6 stars. That is the 7 sisters. And why is it there? It's because that's Taurus the bull, and that's where the 7 sisters, right? relative to that constellation. So the stars, Taurus, relation to the Seven Sisters, that's at least 17,300 years ago. And we just don't think about humanity having that much connection to our past, and yet we do. So the stars are something that bind us. And I think it's important to know that they continue to bind us. It's one of the few things that the entire world is able to work on, no matter what's happening, together, because we do see it as a collective humanity, a part of the expression of humanity to understand. So the three big questions for astronomy I want to talk about are, what are dark matter and dark energy? And I'll try to explain, if you weren't there yesterday, what those are. What is the life history of the universe? And that's because this is a question we can start answering with modern technology. And a question that I think DJ would have talked about are, what are planets like beyond our own solar system? And I'm going to try to link them together because they're linked together by astronomical equipment called telescopes. So discovering planets around our stars is something DJ did for the first time. And what he was able to do is to make measurements very, very precise of the motion caused by a planet going around its sun, because there is an equal and opposite reaction as it goes around. And so the sun actually does a little circle as the Earth goes around it, as does every other sun with its planet. And so by building a very precise instrument, and this is the modern version of what most of the work has been done with, this is a spectrograph that is able to measure the motion of a distant sun to better than 1 meter per second. So 1 meter per second, that's about this. And measuring a star to the same speed that I'm walking allowed DJ and other people to go through and discover planets for the first time. Still used today, but it's only one way that we have of looking at planets these days. The other way is using new technology, and here is a laser going up into space. And we do that because telescopes have trouble looking at stars really clearly, because the atmosphere essentially creates turbulence, and that turbulence creates a twinkling in the stars when it's really bad, which your eyes can see. Or when you take a picture of it, it just makes them fuzzy. Fuzzy means that you don't get nearly as sharp of images as you might otherwise. So you can build telescopes in space, or you can go through and use these lasers to go through and literally sharpen images. And here is an image taken in one of the first systems where you have, this is not Saturn, this is Uranus, in the infrared, and you can see a normal image, and it's kind of fuzzy, sharpened right up with this laser. And this laser goes through and uses some fancy optical techniques and a big mirror that has 1,000 actuators on it, where you literally bend the mirror to take out the bending of the light from the atmosphere. And it has to do that about 1,000 times per second. And when you do it, you get these amazing images where these 10-meter telescopes, which are bigger than any telescope in space, then can produce sharper images than you can with the telescopes in space. So this is an example of what you can do. So this is the system on the VLT Chile. And what you can see is a image of a nearby star. This is a star very similar to the Earth. It's a G star, as we call it. Or, sorry, very similar to the sun. And you have gone through and used optical techniques of interferometry to remove the sun. And then two planets, basically a Jupiter and a Saturn, in this case, you can image directly. And we're making these better and better through improving the lasers. We're not using one laser now, we might be using 5 at a time. And we're going to be building larger telescopes. So we can literally go through in the future and image directly planets. And it's easier when planets are young, they tend to be brighter. But this is something that is just recently happening now. You can also use telescopes that aren't optical, that are and in the microwaves. This is Alma, also in Chile, run by the US, the Japanese, and the Americans. This looks at solar systems not when they're old, but when they're young. And so this is a recently formed star that has been imaged, and you can see the planets going through and sort of snow plowing through dust around it and building up. So this is allowing us to see how planets are forming and building up that process of planet formation. And as I said, we have these next generation telescopes. The giant Magellan Telescope is one of them that ANU is part of, and literally multiple laser systems to go out and allow us to go through and get ultra sharp images, 7 to 10 times better than you can do with the James Webb Space Telescope. Now, the main method that we use now, it's called transiting. So here's a picture of our sun with Venus going in front of it. And you can imagine when Venus went in front of our sun, if you were on the other side of the galaxy, you'd be looking at the sun, and the sun would have gotten just a little bit fainter when Venus went in front. And it's pretty easy to calculate. That's one you can kind of do almost with high school geometry. And so we have had dedicated probes in space, Kepler, for example, that have gone through and literally looked at thousands upon thousands of stars and found thousands upon thousands of planets. And so this is sort of the final catalog of Kepler. And you can see every blue dot and every yellow dot there are planets. And you can see where Earth, Neptune, Jupiter are there. And you're not quite sensitive. So you might say, all right, what's going on here? Earth, 365 days. There's really nothing there. Is Earth incredibly rare? This is sort of the airplane that landed in the UK during World War II. All the bullet holes were in certain places. We do not yet have the sensitivity, it turns out, to find most Earths, because the fraction of time they go in front of their star is so low, you really need to look for much more time, many more stars to build up. But what you're seeing is that there are lots of planets. And as near as we can tell, there's about at least one Earth-like planet per solar-like star from these measurements. Now, most stars in the universe are sun. They're actually 5 to 10 times smaller. And so there are a lot of, it turns out, Earth-like things around what we would call M stars that you could imagine life being on. And the nice thing about M star is our sun only lasts for about 10 billion years. And M star lasts for trillions of years. So your chance of getting life, if you wanted to choose a place to be born, M stars would have been my choice, because we know we've only got a couple billion years left on our sun. So, time's running out. I know we've only been here 100,000 years, and 100,000 compared to a billion is actually a lot. But it does seem kind of final how little a billion years is. So we have new probes going out. We have TESS has been launched by NASA. Plato is even a bigger experiment in space to go out and find these planets. And TESS, for example, has a huge imaging system, and it can provide essentially around nearby stars Earth-like planets. So that kind of dead zone that I showed you of Kepler, you can literally find Earth-like analogs around the brightest stars in the sky. And the reason we want to do that is because we want to go and follow these discoveries up. Right now, you can see this is the Exoplanet Catalog. There are officially 5,332 planets beyond Earth, beyond the solar system. And that includes 3,931 stars. Many have multiple objects in front of them. And that number keeps growing literally every day. So if you think, when I started at Mount Stromlo in 1995, so that was when I started my astronomy career as an independent researcher. That's the year Didier discovered the first planet. We had one in 1995. Took a few years for people to believe it. Now we're up to 5,000, and it's going up very rapidly. So what are we going to do with these? So this is, again, Venus transiting in front of the sun, but a much better picture. And I want you to look at this picture, and you can see it's not been photoshopped. There's a ring of light. That's light refracting through Venus's atmosphere. And so that light is going to, as it comes through, pick up the fingerprints of Venus's atmosphere through the chemical imprints that they do. And these giant telescopes we're building are going to have the sensitivity to go through and see the fingerprints of all sorts of things. And so this is the grand idea of all telescopes. The extremely large telescope of the European Southern Observatory. And it's a 39-meter telescope, and it is well on its way to construction. So we expect it to kind of finish up in the next 7 years or so. And it will be able to go through and, for example, look for the chemical fingerprint. This is a spectrum, so the light spread out from blue to red of the sun. And each line there is a chemical line within the sun, except there are a few things that aren't that way. So that's hydrogen in the sun, that's sodium in the sun. But up here at the top, you can see kind of a funny pattern. That funny pattern, which is, you can barely see, but you can see there's a bunch of faint lines up there. That's the oxygen in Earth's atmosphere that has, as the sunlight has come through the Earth's atmosphere, it's been absorbed. And so the light traveling through a distant, it's in front of its star, it will pick up whatever is in the atmosphere. And if there's oxygen, you will be able to pick it up with these big new telescopes. They have the sensitivity. So that means we're going to literally be able to look for the signatures of life, because oxygen is in Earth's atmosphere because of life. It would not be here otherwise. And if you're making crazy things like fluorocarbons or something, you're going to pick that up too. So that's really exciting, I think, is one of the big questions that we are going to be answering, not in 100 years, but during my life. The life history of the universe is another question. This is because the universe, as I'll show, has a finite life. So if you want to go out and start understanding the universe, one of the first things you need to understand is how big is it? And we can measure distances by looking at how bright objects appear. The further away an object is, the fainter it appears. And it turns out that when people went out and looked at objects, galaxies, they found that the light was stretched redward to what we call a redshift, but it's effectively the like the Doppler shift, or as I'll show you, it's actually the stretching of space itself. But when we go out and we look at a distant object, we can measure how far away it is by how bright its stars are. And we can measure its velocity, essentially by the red shift or blue shift, if it were moving towards us, of its light. So it was found that almost every galaxy in the sky is moving away from us. And in 1929, Edwin Hubble went out and took these two measurements and made a diagram called the Hubble Diagram these days, where he plotted how bright an object is, so nearby objects, faint objects, and then its velocity, and you can see almost everything is velocity away, low redshift, high redshift, and it's not particularly beautiful. I think your average student would be trying to maybe fudge the data a little bit better in their lab book to get a better curve, but this is what astronomers put up with. But there is a trend, the further, the farther. And it is from that that Edwin Hubble went out and said, the universe is expanding. Why did he say that? Well, here is the universe, and I am going to expand it. I've just expanded the universe by a little bit. And now let's overlap before and after. When I overlap those two images, you see a pattern where everything is moving away from where you've overlapped it. Now, you could choose another place and you'd see exactly the same thing. You see that the nearby objects have moved just a little bit, and the distant objects, well, they've moved a lot more. The further, the farther, exactly what Hubble saw. This is a cartoon form of what he saw, but we do have, as I said, you see essentially the same thing anywhere that you look in the universe. Now, let's think about what that means. The universe is expanding, but I can put the universe into reverse. And if I think into the past, it means that things were closer and closer and closer. And if I go back far, everything will be on top of everything else. The Big Bang. So there is this time in the past where something happened. We call it the Big Bang. I'm afraid I'm not going to illuminate you today what the Big Bang is, because I literally don't know. I know something was the Big Bang, and I know what happened afterwards. So we can go back and look back in time by looking at objects that are very far away. And the Hubble Space Telescope was really one of the first things that really showed what's possible, because it was out in space, it did not have the atmosphere to deal with, and it was able to spend a lot of time, no weather, staring at pieces of sky. And so here is a tiny little piece of the sky, much smaller than the moon, and this is what you see. There are 20,000 galaxies in that little piece of space. Each one of those galaxies contains roughly 100 billion to 1 trillion suns. So there are a lot of stars in the universe. What's interesting here, though, is in between the galaxies, there's still black. And that black is because you eventually run out of time as you look back. The most distant objects in this image, we think are roughly 11 billion years in the past. Now, it turns out if we're Hubble, we can actually use Hubble's law to measure the age of the universe, right? You measure how fast the universe is expanding now, and you can run it in reverse. The James Webb Space Telescope just arrived. Well, it was built to look back even further than Hubble. And it is amazing what it is seeing. It's very early in its days. It hasn't made its deepest image. This is one of its images. And what you're really seeing here are galaxies that go back right to the time as early as we could expect to have seen them after the Big Bang. And so this is one such object, a very red object. We think that this object is probably 13.5 billion years in the past. And we're continually going to be finding ones that are a bit further, a bit further, a bit further. What is interesting is we know that gravity should bring, after the big, so it's going to start building little things that get bigger and bigger and bigger, kind of like a snowball rolling down a hill. You don't start big, you start small. So the galaxies we're finding are bigger than you might expect from our theories. So this is a bit of a mystery that's developing, but it is part, as I said, of being able to literally look back to the life history of the universe to see the first stars and galaxies literally before our eyes with these amazing new telescopes in space. India is partners in the 30-meter telescope. That's why my PhD supervisor, who is now the head of the 30-meter telescope, is in India talking to his partners. So that is a telescope that is designed to complement James Webb Space Telescope and use the massive size of this 30-meter telescope to kind of zero in on those individual very distant objects. And so over the coming decade, we're going to be able to go through and really kind of put a magnifying glass on those earliest stars and galaxies that were formed in the universe and try to see if we can understand how the universe came to be. there are some interesting mysteries, I would say, emerging. The universe is full of black holes. I remember I went to my first astronomy talk when I was about 10, and someone was talking about black holes. Do we really believe they existed? They didn't think so, but maybe they did. And now, of course, we know black holes exist. We have literally direct proof. And we have direct proof through gravitational waves, where gravitational waves are emitted as predicted by Albert Einstein by neutron stars or black holes when they emerge. And it turns out you can predict what they should look like, and you can tell the difference between a black hole and a black hole. You can tell the masses of the black hole. You can tell if the black hole is spinning. You can tell if the black holes are going together this way or this way. You can tell if it's a black hole and a neutron star or two neutron stars. So what we're seeing is there are all of these black holes that start out at 30 or 40 or 50 times the mass of the sun. Not clear that exist. We don't see anything really like that in the Milky Way. And so it's a bit of a surprise to have so many massive stars, okay? So we have even bigger black holes, which we call supermassive black holes. These are objects that are literally billions of times the mass of the sun. And so one of the big mysteries is, how do you bring so much material together? Because the universe is only, as I'll show you, about 13.8 billion years old. And it's just very hard how, when you're rolling that snowball, you have enough time to make something so big. And yet this black hole is in a nearby galaxy, not that nearby. It's about, 30 million light years in distance. How do we had so much time? How has it had time to get as big as it is? So I think that remains a big question for the future. Now, we can go back before stars and galaxies were formed. And we can do that because if you go back closer and closer to the Big Bang, there will be a time when nothing has formed. And so we're pretty sure that 10 million years ago, that's about what the universe looked like. Nothing. It was quite smooth. Gravity had just started to collapse things a little bit, but not enough yet. So we want to go through with these new telescopes to kind of go from then and step forward and try to figure out when things appeared and how stars and galaxies like the Milky Way formed. We do have an anchor, and that anchor is the cosmic microwave background. So this is a picture of the entire sky 380,000 years after the Big Bang. So the Big Bang did whatever it did, and the universe was born. It was hot, inconceivably hot. It was dense. And as the universe got bigger and bigger, it cooled, right? When you pull a piston, it cools. So it cools essentially like a piston does as it gets bigger. And at some point, 380,000 years after the Big Bang, the hydrogen in the universe was ionized because it was so hot. That means the electron was not connected to the hydrogen atom. And at this point, the universe cooled to about 3,000 degrees. And that's the time when the universe was able, the hydrogen in the universe was able to grab its electron. And those of you who do physics know that it's scattering light, and hydrogen is actually almost transparent. And so you have a universe full of electrons, and electrons are like great big, targets that stop all light from traveling. So it's like fog. And then suddenly all the electrons, because the universe cools, are grabbed by their hydrogen, and bam, the universe suddenly becomes transparent. So this is basically a fog bank back into the universe where the fog lifted 380,000 years after the Big Bang. All the bumps and wiggles you see there are the seeds of what become galaxies in the future. So those bumps and wiggles are very small, 1 part in 100,000. So we can put that into our models with a computer, let gravity go, And we get a very clear picture of how galaxies should grow over time, because we literally have the initial conditions of the universe, because we can look back in time and see them. That's pretty cool. Now we can go back before that. And we go back because we know the universe 3,000 degrees, 380,000 years after the Big Bang. Let's go back to 1,000 seconds, to 100 seconds, 10 seconds. And the temperature goes up 10 to the 8, 10 to the 9, 10 to the 10. And the density goes up as well. So the universe after the Big Bang, we believe, eventually at about 1 second, had large numbers of protons and neutrons. We can actually even wind it back a bit before that to get the protons and neutrons, because we had protons and electrons, and you end up with reactions that take the electrons and protons and create neutrons. So we go through at about 1 second, and those protons and neutrons start sticking together through nuclear reactions. And so you end up creating deuterium first, but then the deuterium hits other things and gets destroyed, and there's kind of a balance. And you get a bunch of nuclear reactions of things being created and destroyed, but eventually you end up with a chance where there's enough deuterium, because the universe is cooling, that the deuterium comes together and makes helium. Now, you might want to make helium into something. It turns out you can occasionally get helium up to a lithium or even a beryllium, but you need, if you want to get helium into something beyond that, you need to bring 3 heliums together in a very short period of time. That's how our sun might do it at the very end of its life, where it's even hotter and denser than this time, 10 to 100 seconds after the Big Bang. And so the nuclear reaction creates a very distinct pool of material, of hydrogen, helium, tiny amounts of lithium, but it's very clearly a nuclear reaction that definitively predicts that 75% of the universe should be hydrogen and just under 25% helium. And guess what? We go out and we look, and that's exactly what we see. And it also says there'll be 1 part 10 to the 5 deuterium, there'll be 1 part 10 to the 9 of lithium, and we see that as well. And if you mess around with the Big Bang model much at all, then none of those nuclear reactions work. So we're pretty definitively able to go back to this time right after the Big Bang, thanks to the physics of, I would say, physics of thermonuclear explosions on Earth have led to at least 1 positive outcome, which is understanding the early universe. So one thing that we do is the first stars, the stars made after the Big Bang, they should be made out of hydrogen and helium, but not much else. They should be chemically pure. Now, we have this 100 million stars in the Milky Way, actually 100 billion stars in the Milky Way. Imagine we can go out and look for the chemical pure ones. So that's one of the things that we were doing from a big map of the southern sky with the telescope that we built after our observatory was destroyed, very large digital camera on it. And we were able to put in this imaging the ability to discern chemistry. So we went out and literally looked at, in our case, not quite 1 billion stars, but hundreds of millions of stars. And one popped out that literally showed no signs of anything other than hydrogen and helium. And so this is the most chemically pure star that we know. It still has carbon, which was not created in the Big Bang, but it has no iron at all. Now, stars in their evolution create carbon, but they typically create iron when they explode as supernovae. This star clearly was polluted by some sort of previous star, but what we think happened is that this star kind of fizzled. It didn't explode as a supernova. It actually collapsed to a black hole. And only a little bit of its outer bits got in, polluted this star. So this star has a single, it only has 1 star in its sort of progeny, but that was a star that went direct to a black hole. probably quite a massive star. And so it may account for example, many of those black holes that we saw that we didn't really know would be there. Now, we're not quite sure if we understand the physics well enough to predict why we go straight to a black hole of something of its size, but it's a clue, and it's a way that you can go through and try to understand the early universe based on the fossil record in our stars. Gaia is doing this same idea on steroids. Gaia is a satellite done by the Europeans that is literally measuring 1 billion stars, one object at a time. It's going to be able to measure their chemistry, but it's also able to measure their distance because it has the ability to measure their position very precisely. And so as the Earth goes around the sun, it's able to do parallax. It's able to look at the star from this direction, waits 6 to 9 months, get on this side, you see it the other direction, and voila, you know its distance. It also has the ability to measure velocity when used with other data. So we're literally going to be able with this to piece together the galaxy one star at a time. We'll know every star's distance, we'll know its chemical composition, and what we think is most of the galaxy came together from small little bits. It was built up by little galaxies. So our hope is we'll actually be able to see the little galaxies, kind of the stars from the same little galaxy across the Milky Way. And so it is continuing to take data. It has produced its full map of the sky. Now, this is an interesting picture because that's not a photograph. That's actually every star that it measures. It knows how bright it is, it knows its color, knows where it's at, and it's just plotted down as a pixel, and that's added it all up to make a synthesized photograph from all of that data. So there's 1 billion stars in there, and you can see what the sky looks like. There's a lot of stars. You have the Milky Way. You have the Milky Way through the center. Our galaxy, our two sister galaxies, the small and the large Magellanic Cloud, and then a lot of dust and stuff. And some astronomers like to study dust, but for most of us, it is absolutely a curse because it's there and it's just in the way and messing things. So stay tuned over the next few years as we get all of this data finished over the next 3 or 4 years it'll take. And then we're going to be able to go and see how the Milky Way was built up star by star in this way. So another way that we can look at the early universe is at radio wavelengths. So the radio sky actually has the ability to look back probably before or at the time the first stars and galaxies were. So this is a simulation of what we think the early universe might look like. And what you're looking at here is hydrogen. And the reason you can see hydrogen is we don't really think about a hydrogen atom being very exciting, but you have, it turns out, a spin of both the proton and electron. And if they're aligned, it's at one energy state. If they become disaligned, it's at a new energy state, and you get a 21 centimeter wavelength photon, 1.4 gigahertz if you want to work in frequency. And so that, it turns out, because there's so much hydrogen in the universe, you might expect if there's cold hydrogen in the universe, which we expect to be lots of it in the early universe, you will get a bunch of hydrogen. Now, as stars and galaxies form, they turn out, they put out ultraviolet light, and they ionize hydrogen so it can no longer emit. So around each forming galaxy, you're going to get a little hole. And that's why you get an image that sort of looks like that. That is the places where there are no galaxies, and then the Swiss cheese around the galaxies. So that's a way of figuring out when the universe turns on as well. And so there's a huge amount of work trying to figure out when the universe turns on from radio wavelengths. And a lot of it's been done here in India. So this is a very simple telescope in the middle of Australia. And because you get to look at the whole sky, it doesn't have to be big, even though you're looking back to right back to the Big Bang. And so this telescope made a tentative measurement that I don't necessarily think everyone thinks is real. So other people are trying to go through and replicate it. And one of the biggest efforts was here in India by the Raman Research Institute, Ravi Subramanian. And this is a similar telescope put out in the middle of a lake, up in the middle of India, up north of Bangalore. And it's there in the lake because the lake provides essentially a shield from interference and reflecting radio waves. So that's why it's there, out there. Anyway, at this point, I would say that telescope is not seeing what the first telescope saw. But this is a big industry. And so we are building lots of telescopes, including large interferometers in the Western Australian desert that have literally thousands of tiles like this. So almost coat hangers in the desert. You don't need much. You just need a lot of them. And then they are literally put together. You get little signals from there, and they're put together in a supercomputer, and you form radio images in a supercomputer by essentially combining the information from each of these tiles together. This is a precursor of which, again, the Raman Research Institute was part of this program. But we have, and I know one of the people here is part of this program, Hera, which is another telescope in South Africa, a precursor to the square kilometer array, trying to do the same type of thing. And eventually the granddaddy of all, the square kilometer array, literally a square kilometer of collecting area in the Western Australian desert to go through and look at this hydrogen. A similar very large telescope in Southern Africa to look at other things at higher wavelengths. So we are putting a lot of effort, as you can see, to understand this early part of the universe. And we will be seeing, as I said, the answers emerge over the coming decade. So my final of my three big questions, and they're not the only three big questions, but they're three big questions, is what is this stuff called dark matter and dark energy? So what is dark matter and dark energy? So I've already shown you this diagram. One of the first things, as I said, you can do is if you measure essentially how fast the universe is expanding, you then know you can just run the universe back in reverse. And you can do that using the theory of general relativity. Einstein had this revelation in 1907 that acceleration due to gravity and acceleration due to motion were completely interchangeable. That is, if you were in an elevator, without any windows, you can't tell whether or not it's your motion or it's gravity, or you can be in a rocket, 9.8 meters per second squared. You literally can't tell if you're on Earth or in the rocket if the acceleration. A very simplistic thought that took him 8 years to understand, but when he made everything consistent, he came up with general relativity. And general relativity predicted that space should be curved. And it also, it turns out, allowed it to calculate cosmology for the first time. So space was shown to be curved by Eddington in a thing he did in 1919, where they went out and they took images of a stellar field during a total eclipse of the sun. Then they waited for the sun there and they compared the positions of the stars where they were during the eclipse and out, and the motion, which was caused by the distortion of space being curved, you would think that displaces things like a magnifying glass, was exactly as predicted by Albert Einstein's theory. This is a remarkable theory because normally theory does not just emerge from an idea. Normally you have a problem you're trying to solve, and so you come up with an idea, you iterate, and after about 1,000 iterations, you come up with the next theory that seems to explain that and not break anything. Einstein just had this single idea, and it turns out it has never been shown to be inconsistent with any measurement that we have made. It has predicted gravitational waves, it has predicted black holes, it has predicted essentially the cosmology that we see, gravitational lenses I showed you earlier from the James Webb Space Telescope, all of that predicted in advance from a single idea. We're often told that's the way science is done. It's never done that way. I can only think of Copernicus saying, aesthetically, I think it makes sense for the sun to be at the center. There was no reason for him to do it. His theory did not predict the motion of planets as well as the Greeks, but it was aesthetically pure. And then Einstein having this idea is, I think acceleration must always be interchangeable with gravity. So it's a remarkable time and a remarkable theory. And one of the remarkable things, in addition to making Einstein famous for forevermore, is it did allow Einstein to do what Newton never could do, which is to solve cosmology. So Newton was a funny guy. If you ever get a chance to go to Cambridge and get to read his notes, you realize probably glad he was not your neighbor or something, because he was a very funny guy. And Newton was obsessed about trying to figure out how to calculate what would happen in a universe that goes on without end. And it turns out there is a solution to Newton's laws of an infinite universe, which is the universe is empty. There's nothing in it. There's no other solution. You can use Gauss's law if you want to do it to get that solution. It's a very easy way to elegant way to do it. So he knew he was there, and it really bothered him. And of course, it's because his theory was in. Einstein's theory of general relativity does allow you to calculate things in cosmology. And when Einstein did it, he got a problem. He had a problem. His solution that it was changing in scale over time. And he looked around and said, the universe seems static to me. So he put what he later called a mistake, what he called the cosmological constant. It's an integration constant in his theory. And it could be there. It didn't change it at all, but it was sort of a little factor and extra stuff. And what he thought is that he could tune this cosmological constant to a value, because it turns out it makes space push on itself. It's like repulsive gravity. So his idea is you tune it to match the matter in the universe, its gravitational attraction, and balance it out. Now it turns out it's unstable. That is if a butterfly flaps its wings in Andromeda, it sets the universe into motion and it won't be stable. So it was not actually a solution to it, but like most things in Einstein's world, his mistakes were still actually pretty good discoveries themselves. So Einstein was quoted as saying, I was acting like a donkey because he stuck with it late in life. And I'm glad that he did stick with it. But Einstein's theory of relativity, as said, allows you to essentially go through and predict what the distance is between galaxies. And in an empty universe, the very simple universe, it's just a straight line. It's just like Newtonian mechanics. And if you throw a ball up without any gravity, it just keeps going straight, right? It's there. So if you can measure how fast the universe is expanding, you can run it in the back. This is tied, it turns out, to how much material there is in the universe. And the universe is complicated because gravity curves space. So a simple universe, turns out, is not flat. This is a universe that has a lot of stuff in it. It has a density that we say is a critical density. So if the universe, you want to have the universe be flat, that is, triangles add up to 180 degrees, which is how things are here locally. Of course, if we try to do a triangle between Australia, India, and Uzbekistan, the triangle adds up to more than 180 degrees, and that's because Earth is curved, right? We don't normally think of it that way, so it's flat locally, curved globally. So Einstein's theory of general relativity tells you that there are many universes you can have. A just right universe, a heavy universe, and a light universe. So very light universe, one that's empty, will actually have the shape of a hyperbola, a saddle. A heavy universe curves onto itself, finite in space and time, it turns out. And a just right universe that has the perfect amount of stuff where the universe effectively is balanced on a precipice. That's what gives you a flat geometry. And these things then allow you to go through and essentially fit curves to what you see in the universe. For my PhD thesis, I measured how fast the universe is expanding locally, just like Hubble. And here I am with Bob Kirshner, wherever he is. I think he's in Bangalore right now. Hello, Bob. Here I'm showing him 1993, my results. And we extrapolated it, assuming the universe was empty, which is the simplest thing to do, and the age of the universe about 14 billion years. So we've refined that measurement now. And I should say, I do not get credit for measuring the age of the universe. I was part of a very complicated conversation in 1993. It was the Hubble Key project that came along. They fortunately got the same answer I did, or I fortunately got the same answer they did, but about 14 billion years. We now think it's 13.8 billion. Now, as I said, the theory of general relativity gives you a few other trajectories you need to worry about. If the universe is full of material, it's going to slow down. Just like if I throw a ball up from Earth, gravity slows the ball. So it will be in a different trajectory. So the universe, if it's heavy, might well not be as old as 14 billion years old. And what happens into the future, of course, is very much dictated by how much stuff there is in the universe. A heavy universe will actually reach a maximum size, start to collapse, and end in what I like to call a Gnab Gib, the Big Bang backwards. Whereas a light universe just keeps getting bigger and bigger forever and ever. So when I moved to Australia in 1995, it was because I got a job there, and I got a job there by pitching a fairly outrageous thing as a 27-year-old. I am going to look into the universe's past, and I'm going to measure how fast the universe has expanded back in time. And so the idea is that if I look at very, very distant objects and measure the expansion rate of the universe by measuring distance and redshift, and then I measure the same quantities of nearby objects, making a few corrections along the ways that you have to, I could see is the universe just coasting along. That is it not changing over time? That's an empty universe. Or is the universe heavy? Is the universe following a trajectory that is either on this side of that just right line where the universe is flat, or that side of the line where the universe is infinite and goes on forever into the future? So that was my pitch. I'm going to measure the ultimate fate of the universe. Seemed like a good idea. So the key technology that allowed me to make that ambit claim was the understanding that type 1a supernovae, thermonuclear detonations in space, go through. They are about 5 billion times brighter than the sun. They create the iron that's throughout the universe, including here in Australia. We like to sell it to places like India. Thank you very much for my supernovae. Haven't got the government to invest in me yet because of that, but they probably should. So it was the understanding from a group in Chile that went through, took exquisite data, and was able to calibrate these objects to a few percent in distance. So that was a real great technological innovation. And these objects are worthwhile thinking about, because if you go through and you look at a star like the sun, at the end of its life, it will form a white dwarf star. That is the compact core made up of carbon and oxygen, about the radius of the Earth or even smaller, and usually about 7/10 of the solar mass. If you have the sun born as a binary, then at some time in the future, those orbits that turn out decay because of gravitational waves, and they will merge. And Chandrasekhar in the 1930s realized that the gravity will overcome essentially electron degeneracy pressure at 1.383 times the mass of the sun. And so if you exceed, when you merge 1.383, then you will get a giant thermonuclear bomb, because gravity will try to squeeze this thing made up of carbon and oxygen. Carbon and oxygen will come together, create nickel-56, and produce a huge amount of energy through gamma rays. You produce a lot of iron because nickel-56 decays to iron, and you create a big ball of iron and about 5 billion suns worth of energy leaking out over a period of several weeks. So quite exciting objects that are very bright. You can see them a long ways away, literally 10 billion years in the past. And that is what we were able to do over a 3.5-year project, was to go through and measure the distance back in time. And here is our data, the nearby objects, the distant objects we did with this experiment. And it's not a particularly flash diagram, just like Hubble's was. But if you go through and say, what is the chance that those objects are down here? It was less than 1 part in 10,000. It's about 1 in. And that's convincing at some level. But a group in Berkeley was doing a very similar, led by Saul Perlmutter, had basically the same statistical significance from an independent group of objects. And so together it became more than a 1 in 100,000 chance. And at that point, again, doesn't quite reach the 5 standard sigma, the 5 sigma criteria, about 4.5 together, but certainly pointed to a direction that the universe was speeding. And it's that, of course, that we won the Nobel Prize for, because it would appear the universe was speeding up rather than slowing down as we had expected. And our best way to understand it is Einstein's mistake. Energy that's smoothly spread through the universe, we call it dark energy, but it's really the cosmological constant, unless it changes a little bit. And it thus far has been something that has been made predictions that we can test. And so here are the teams. It's worthwhile noting 60 people did the work that 3 of us won a Nobel Prize for. So if you ever meet one of my team members or one of Saul's team members, please give them a pat in the back and say, well done, okay? Because they did a great job. Now, Einstein allows you to go and calculate a new set of curves. And those new set of curves, it turns out, looks like the red line. Dark energy is fixed in time and space. It is the cosmological constant. It doesn't change. Space expands, its density stays the same. The density of you and me as I go back in time when the universe is smaller and smaller rises, as the volume of the universe shrinks. And so you have a time, it turns out the universe right now is being exponentially pushed apart. But when I go back in time, the universe actually starts slowing down if I go back in time enough. And that's because the dark energy stays fixed. The atoms that we're made of become more and more dense. So the gravity due to what we're made out of, and it turns out dark matter, which I'll talk about in just a sec, overwhelms the dark energy if you go back in time. So the universe after the Big Bang, we think slows down, kind of like your intuition would say it was. It gets to a certain density where the density of the cosmological constant is bigger than the atoms in dark matter, and then the universe takes off exponentially. So it's a funny curve, but that is the curve that the universe appears to be on. And it's a very precise curve. You can go out and measure and see what you get. Now, one of the easiest ways to measure that curve right back to the beginning, right after the Big Bang, is to the cosmic microwave background. The cosmic microwave background is a bunch of sound waves propagating through the plasma of the universe. So think of it as a big pond of material. And the Big Bang was like throwing rocks into the universe. And so depending on what the universe is made out of, the wave pattern is different. So if the universe is made out of atoms compared to photons at different ratios, you get a different wave pattern. So we have gone through and been able to measure the wave pattern very accurately. That wave pattern, the theory is the line. The data is essentially how many sound waves we have of different size on that image. And you can see the theory is really terrestrial physics. It's sort of like doing sound waves bouncing around in this room. It's not simple, but it's completely tractable. And it's very rare in physics that you get a curve fitting data quite as well as that. And that is beautiful. And what does that curve tell you? It tells you the universe is 5% atoms and 25% something called dark matter. Dark matter. We haven't talked about dark matter yet. I've alluded to it. Dark matter is stuff that has gravity, but it is literally invisible to everything. It goes right through everything. It goes through atoms. It goes through the Earth, probably goes right through a neutron star. It literally does not interact with it. Easy to calculate, it turns out. It's gravity. It's your in-body calculation where you just do 1 over, sort of 1 over r squared, and don't worry about things colliding. That's what the stuff is. And it turns out, if it's not there, you don't get anything right, looks at all like the data. If you add it, it's there. And it turns out we have been adding this mysterious dark matter since the 1930s, because everywhere we look in the universe, we see gravity, and we see atoms, and we see there's always like 5 times more gravity than there are atoms. So we've always invoked stuff called dark matter, and this is sort of a way of definitively showing it's there. So whenever you meet someone who has a says, I have my Mond theory, which is a modified Newtonian dynamics theory that says I don't believe in dark matter, tell them to fit that, because that is what you're trying to fit, nothing else. That is the only thing that matters, in my opinion, these days. Now, the sound waves have a size. You can measure them in meters. The universe, as I said, is curved, or might be curved. And so if it's curved onto itself, that magnifies the scale. If it's curved the other way, like a hyperbola, then it demagnifies. And if it's just right, then everything kind of runs on straight lines. And so you can predict how big those sound waves will be depending on the, essentially depending on the curvature of the universe. And remember, the curvature of the universe is telling you how much stuff is in the universe. So the geometry of the universe, the bumps are going to be much smaller if the universe has this shape than this shape. But it turns out it too, 1 part in 1,000 is flat. It has the shape of being exactly right, just right. So when you put it all together relative to a just right universe, I've already told you everything has to add up to 100% because the universe appears to be flat. 25% of it's this stuff we call dark matter, 5% is atomic matter, the atoms, leaving you with 70% mystery matter. That's the dark energy, because the dark energy contributes to all matter, just like atoms do. And so it's another way of getting to the same thing that we measured in 1998 at Supermassive. So we have a messy universe that 95% of which is not stuff we see here on Earth. Now, you may think, if you have to make up 95% of the universe, doesn't that just mean you don't know what you're doing? And you'd probably be right. But we can predict things. And remember, this is the model that predicted in advance exactly that very complicated curve. But we can also go back and say, how does it predict if you get more data on things like supernovae? So dark matter is a mysterious substance, and this is something known as the bullet cluster. And it sort of shows, I guess, the property where if you take 2 clusters of galaxies and have them run through each other, you expect the atoms to collide and the dark matter to kind of pass through. You can see where the gravity is because gravity distorts space. And so you can see essentially bending properties in the distant galaxies and make a map. So this is a map in pinkish red of atoms measured by X-rays and gravity measured in blue by gravitational waves. And you can see the atoms have collided in the center, and the other stuff seems to have just gone through. Okay, somewhat controversial, but kind of shows you the basic idea. So how would you go out and try to understand what dark matter is? Well, in the Large Hadron Collider, you might hope that by banging things together, you would create it. Now, we don't really know what it is. There are some theories that say you might create it. And how would you know it's there? Well, you would have a series. If you think about how the Large Hadron Collider works, you collide things, and then they literally measure every particle that comes out of it, and they kind of add it up, and they say, boop, 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 boop. Okay, that's there. If there was dark matter, the dark matter would not interact. So you'd create something, boop, boop, oh, something's missing. And you'd see that again and again and again. Now, we have not seen that yet, but that's how you might see it in the Large Hadron Collider, where things were escaping the detector for reasons that didn't make sense. There was like something crazy happening and things gone missing. Another way is through direct detection. So we hope, and I hope, that dark matter occasionally interacts by some means other than just gravity. Because if it only interacts by gravity, we're never going to detect it on Earth, right? It's just, that's it. So the idea is you put things, for example, liquid xenon, tons of it, underground, so nothing else can. Dark matter will come through and interact very, very rarely with the xenon. And when it does it, it makes what they call a phonon, kind of a ping. And you could detect the phonon and say, ha, we have caught that really, really rare interaction between dark matter and xenon. And various theoretical dark matters candidates, you should be able to measure this way. At this point, nothing. We've been doing it for many years with larger and larger experiments. But that goes on. The other way to do it is through astrophysical detection. You might hope that dark matter sometimes interacted with itself. And so there was a lot of excitement a few years ago because there were measurements of essentially particles out in space, one of the space station experiments where there were a lot of particles. We did not understand why they'd be there. So they were able to start mapping it out of where these positrons were created. And I think the best guess now is those were not created by dark matter annihilations, but rather in astrophysical objects. Pulsars is probably where they are. So at this point, we still don't know what dark matter is. We're trying hard, but nothing. So dark energy is another thing altogether. The only way we know how to look at dark energy is to see if it does what Einstein's theory predicts it will do. So is the universe being accelerated like dark energy predicts it to? So here is what the supernova data looks like. It's not a small little bit, it's a lot. And the best fitting data, exactly consistent with that from the cosmic microwave background, goes through there. There is no signal there at all. The data are exactly consistent with a cosmological constant, best as we can do this. We have other ways of looking at this. Those sound waves in the early universe get imprinted as sound waves in the galaxies that are formed. And so you can go through and essentially look for that pattern in galaxies by doing big surveys of literally millions of galaxies. And we've done that now. You can go through and see the sound waves imprinted in the galaxies through things like the Sloan Digital Sky Survey and some surveys like Wiggle-Z down in Australia. And so that is the acoustic signal that you get from the galaxies. It's not very exciting, except for probably an astronomer, but it is exactly what you would expect, again, from Einstein's theory of general relativity, a cosmological constant of the 70-25-5 ratio. Nothing exciting. So we continue to look with new experiments. Euclid is a program to go out and do doing lensing and again, these acoustic oscillations in galaxies. WFIRST, similar, with some supernovae thrown in. And all of them are looking for little defects in the theory. I'm not optimistic that we're going to find anything. So I think we're going to have to look forward to some very bright Einstein-like person to think of a theoretical explanation of what's going on with dark energy. Because there is less than a microgram of dark energy in the entirety of Earth. There's no way of directly detecting it here on Earth. So in our future, well, as I hinted, our sun only lasts for 10 billion years, but it already is over halfway through its life and its nuclear engine is getting hotter and hotter. So our oceans will boil sometime in the next 1 billion or 2 years, and eventually we will be swallowed up by the sun as it expands. So we do need to be thinking about Plan B, and it's not Mars, in case you thought it was Mars. It's not Mars. But the future of the universe is equally grim. The future of the universe is dark energy, and that's because the more space expands, the dark energy stays fixed, and it can continue to push on itself as the universe gets bigger and bigger and overwhelm gravity. This creates essentially exponential expansion. Inflation if you're an economist, inflation if you're an early universe person. And so the universal expansion goes faster and faster, and the creation of space actually happens more quickly than even light can travel. And so we expect to be isolated from the galaxies we see today, where the light they emit is trying to get to us, space is being created, and the photons emitted from galaxies we can see today will never reach us in the future. That is already happening. If you look at that image from the James Webb Space Telescope, most of the galaxies in that image, the light they put out today will never reach the Earth. We are already stranded from those galaxies. And so in the fullness of time, we look out, and first the galaxies that are a long ways away disappear, and then the nearby ones disappear until there is a sort of sphere around us of about maybe 50 galaxies that will all kind of become super galaxy. We have essentially our not expanding, right? It's a part of the universe that will collapse. The Milky Way collapsed 13 billion years ago, and other little galaxies are collapsing now. And the little sphere, it has the Andromeda galaxy, a few other ones. We'll create a super galaxy, and we'll look out, and there'll be no other galaxies due to cosmology. Now, if you go even beyond that, we think eventually the stars will start evaporating off the Milky Way, and they'll get isolated on their own in the expansion. Eventually, the black holes will decay, and then we'll have, we think, probably the proton eventually decays. And when the proton decays, which is a long time in the future, everything breaks into individual particles, like electrons, like quarks, and they become isolated from every other particle in the universe. So the universe ends up this death where everything is separated from everything else beyond the ability of any information to come to us. So unless we absolutely understand everything about the cosmos, extrapolating that far into the future is dangerous. But that is the best explanation we have. So unless dark energy, though, disappears, I think the first part of that story is right. We look out into a universe that effectively disappears over time, and cosmologists like myself end up out of business because there's nothing left to look at. Thank you very much.
Professor Schmidt. Thank you, Professor Schmidt, for a wonderful and inspiring lecture. The floor is now open for questions. I would request those of you who have a question to just raise their hands. Kindly speak into the microphone after it has been brought to you. If you have questions, just raise your hand, please.
Good evening, sir. Thank you for the talk. So I'm Rishabh Srivastava, fourth year undergrad. So my question is, I have like two questions. Firstly, to start with, it's related to equation of state of dark energy. Currently, I guess the currently accepted value, it's like -1. I mean, how would the universe change if we were to find out that the equation of state, the constant, it is like not constant, but it's like changing with time? How will the universe change?
Yeah, so when I was showing you all that data, that was specifically to measure how the expansion rate of the universe changes over time. And for the non-cosmologists in the audience, the property of dark energy is essentially what we would describe as equation of state. And it's how you would go through and measure how much the density of the cosmological constant or the dark energy changes as the volume of the universe changes. So that's effectively what it's measuring. -1 is a universe that this stuff does not change ever over time. So there are the ideas that maybe this is part of a field of some undiscovered particle, and so it would change and evolve over time. So that's why we're trying to measure it. And at this point, we know it's very close to -1 as over the range that we can see. If it were to be different, then the expansion history of the universe will differ a little bit. The universe will be a little further away at a given redshift back in time, or a little closer, depending on how it's changing. But it would be profound, because then it would tell us it's not the cosmological constant. It is something like a field from some sort of remnant particle, and our particle theorists would love that. They'd go in and be able to go through and invent lots of things. The challenge is the energy scale means it might be almost impossible to ever measure here on Earth. The only way you'd probably get a glimpse at it is in the time right after the Big Bang. And there you might hope to see it in distortions in the cosmic microwave background that I haven't talked about today. Maybe a future lecturer can talk to you about what we call B modes in the cosmic microwave background. But that's another hour and a half to get to that.
Thank you. Your question.
Good evening, sir. I am a PhD scholar. In your graph about the predicted model, you showed that initially there was 0%, when after the Big Bang, there was 0% dark energy. Now there is 70%, and eventually it will reach a time when it is 100%.
That's correct.
So actually, in that case, what is happening to the matter and the dark matter? Because dark energy has a totally different, dark energy is repulsive in nature, whereas matter and dark matter are attractive. So what's happening to the dark matter, these two species?
Yeah, so we're sitting here and we go, you know, essentially what happens to us is we remain as is, but as space around us gets larger and larger, the horizon gets further and further, our density asymptotically goes to 0. So it's just because we become the one thing in an infinite universe, effectively. That story at the end, you or our galaxy ends up being the only piece of matter and dark matter in a universe that is completely otherwise empty. So that's why our matter, our density effectively asymptotically goes to 0.
So is
It
it
never effectively goes to 0, 0. It asymptotically goes to 0.
so possible that because dark energy is increasing, the light now is the just right universe. So from that, it will move into a heavier universe.
Well, we do have general relativity. And so the only way the universe is going to suddenly change trajectories is if either relativity is wrong, and then if general relativity is wrong, I don't know what's going to happen. This is my only way to understand this. Or 2, if some magical new form of matter appears out of the vacuum, well, that would change the trajectory. Or if, for example, dark energy suddenly decided to decay because we don't understand what it is and disappear into a bunch of photons, that would change the trajectory of the universe. But we have to kind of rely on general relativity for the trajectory of the universe because it's the only thing we really know. But it's, if you start making things up that can happen, then anything can happen. But you got to have a reason to make things up, right? And when you do make things up, you better be able to predict something so that I can believe that, the person who says the universe is held up by, tortoises walking around is wrong. It's kind of hard to show that they're wrong, but I'm not sure I believe them. The point being, the scientific method, there has to be, I guess, reasons to believe the simplest model. The simplest model right now predicts everything we see, more or less. There's a couple little cracks in it, but I think that's how the scientific method will go, is not making up stuff, but trying to look for cracks in the model that we have to add things to explain. So that's where I think.
Thank you. Thank you for your question. Go ahead.
Hello, sir. It was a really nice lecture. I would like to say that it was a very well delivered one. So my question is basically more about particle physics and astrophysics together. So you said that universe was built about the timeline of universe. There was a time when the universe had a sea of electron that made it foggy. But my question is, why was there majority of electrons and not other kind of particles, not other kind of fundamental particles?
All right, I'm going to need a little help on. I couldn't quite
So
pick it up.
I think the question was, were there other fundamental particles prior to recombination
Yeah.
which were interacting with photons and not just electrons? What were they doing?
Yeah.
Okay, thank you. So the universe has gone through a bunch of phases. So there's, let's go back. The time after the quark-gluon phase, we got into a phase that looks like the modern era, where you have essentially, neutrons and protons. But before that, you had interactions between creating pions and everything that the Large Hadron Collider essentially creates. So they were in a big thermal bath, and you were having essentially the reactions of one type of particle into another and then back and forth. But as things cooled, then things froze out, and you got, most of the pions and stuff disappeared because they found other pions and essentially created photons. And then we got left at the very end with protons and electrons. They were able to form about 1/7 of them came together to break neutrons in that thermal bath. Then that reaction got frozen out. And then you're just left with the protons, neutrons, and electrons, but there were no nuclear reactions. So at each stage, you have an equilibrium between everything in the universe that can be at that energy being made and destroyed. And as I said, it's an equilibrium where things get frozen out as the universe cools. So it only lasts for about 1/1,000,000th of a second, but it's up to the quark-gluon phase. We kind of understand it because we got the LHC. You want to go before that, then we're starting to make things up because we don't know what happens from any way. And I don't think the theory, if we would have suddenly started seeing supersymmetry in the LHC, it would say, oh, we can go up a bit more. We haven't. So we don't really know what happens above a couple TeV because we just don't have any experimental data.
Thank you, Professor Schmidt, for this brilliant lecture. I work in cosmology, mainly in the areas of early universe.
This is
my name is
dangerous,
Hera. Yes, he was my supervisor. Actually, my question is, what is your stand on the Hubble tension between CMB and the supernova measurement? Is it, would you prefer systematics as an explanation or new physics? Thank you.
So that is a good question. I talked a little bit about it yesterday. But so there is a crack emerging in this model where when we measure how fast the universe is expanding from, for example, supernovae right now, that's a very hard measurement because of things like dust that I've told you in the universe. It's a mess. And when we measure that from the cosmic microwave background, when we go through and we fit the acoustic waves, we get essentially a measure of the state of the universe that's quite accurate at that point. So the measurements that we have when we extrapolate that measurement from 13.8 billion years ago to the present is different by about 8%. And it's 8% plus or minus 2, 2.5, depending on how much you believe. So I'm always a bit of a skeptic because I know how hard it is to do the nearby universe. But I have to admit, I've gone through and done my best. I had a PhD thesis who blinded everything and literally got the same answer. So I do think it's becoming something to really worry about. I don't my guess is it's not system X. That means there is a little glitch of that's a 7 or 8% level. Am I willing to, bet my life on it? No. Am I willing to bet my dog on it? No. Would I be willing to put $100 on it? Yes. So that's my level of certainty. So I do think there's an issue there. I do think we need to go and measure as accurately can, and I think using gravitational waves of neutron star mergers and the waveforms, probably the cleanest way I can think that's completely different than how we've measured it right now. But that's a 10-year proposition. That's probably what I'm going to be working on when I finish up as vice chancellor next year. The other thing, as I said, there's a little crack, is that galaxies are coming together faster than I think you can really understand. And I am worried about supermassive black holes at a redshift of 7 or 8 that were out there. And I'm just wondering, are there primordial black holes, that is black holes born at the time of the Big Bang? And what does that mean? And I think we need to try to understand if it, that's kind of a novelty, but doesn't actually matter, or there's something else that's allowing the universe to evolve much more quickly after the Big Bang than otherwise we would have thought. I don't know. There's some mysteries there. And as I said yesterday, I'm very pleased to have some things that are broken because it gives us something to work on. It's pretty mind-numbing to create 10,000 supernova sets. We have 100 people working for 10 years, and you at the end of it go, yeah, we got exactly what you got in 1998, just much more accurate. So I think it's good to have cracks because they give us some chances, hopefully, to understand this. It's not sufficient. So the tip of the red giant branch, which is another way of measuring distances, I think it's telling me that it's hard to measure distances in the nearby universe because of dust and things. And so it hasn't convinced me there's not a problem. It hasn't convinced me there is a problem. That's why I think we need to have something very clean. And that's why I think the gravitational wave looks pretty clean to me. It just requires 10 or 15 years worth of work to get it right. I'm 55. That'll be my lifetime project.
So we will have one question from the audience here because we have students from outside. They are attending from other halls who have questions too. Please go ahead.
Dear Professor, I love this wonderful talk. I have a couple of small questions. The first one is like, in one of your slides, I could see like, primitive stars discovered and why primitive Earth or similar kind of planets can't be discovered, whether it is absorbed or sucked by the star itself.
Yeah, so one of the interesting things, imagine trying to create an Earth out of that very primitive star that I showed you. It has no iron. So there's no Earth going to be formed. So what we do know is when you go to early in the universe, there's not enough metals. Astronomers call anything a metal. There's not enough stuff to make an Earth-like planet. Now you'll have gaseous planets, but there does to be a correlation between when you're going to start getting planets. So the first group of stars, before there's iron in the universe, there's not going to really be any planets because they're just nothing to make them. So they do evolve.
One more question with the current situation. What is your opinion about mining in the space, going to meteoroid?
So I give that as a mining in space. I give as a problem set to my bits, and I have them do the cost benefit, try to figure out the scenarios and do it. And I would say there's a lot of stuff on Earth. So I think the only thing you're going to mine in space are things you want to use in space. So for example, mining water in space to create rocket fuel in space probably makes sense. If you want iron in space, you could imagine smelting and making steel in space because it costs like $10,000 a kilo to get it up to space. But it costs about $10,000 a kilo to get it from something. And even, something crazy like osmium, which is really expensive. There's only about 100 kilos used a year on Earth. So it's not worth spending $100 billion to mine an asteroid. So anyway, come and take physics for decision makers at ANU, and you too can do that problem.
So there are a couple of questions from the students from outside this hall. One question is, if the universe is ever expanding, why is there no major change in the distance between Earth and Sun?
All right, so that's actually a good question, and I haven't really covered it here. So when you look at the universe, and I covered it kind of at the end, our part of the universe is dense. So right after the Big Bang, we had enough density that the gravity stopped the expansion of the universe around the Earth, around the Milky Way, and it collapsed and it formed the Milky Way. So that part of the universe is no longer expanding. All right, it was started expanding at the Big Bang, but it stopped. And so, as I indicated, there are these spheres where effectively you have more than the critical density that I referred to as the just right density. Whenever a sphere in space exceeds that critical density, it will eventually stop expanding and collapse. Okay. Now, there's a little bit there where it turns out it can get hung up as the universe accelerates, and it's not quite clear, but there is essentially a critical place where you stop expanding. So we're a place that's just too dense. And so our part of the universe quit expanding 13.5 billion years.
Thank you. So one more question. How can different planets in the same star system be differentiated from each other?
Okay, so it turns out that if you've got, for example, the way DGA would have shown you with essentially the radial velocity, where you measure the Doppler shift very, very accurately. Well, the Earth takes a year to do its little curve. Mars takes 2.5 years. Saturn takes 17 years or whatever it is. And so you can actually just do lots of measurements and see sine waves on top of sine waves. So that's how you do it. In the case of stars that are transiting, you'll see a transit, and then you'll see a different shaped transit because it's a different size planet. So there are different ways to do it that way. And then the imaging, you get to see them. I showed you 2 planets there. You just image them and see them in different places.
Maybe I can have one question from here. Yeah.
Thank you, Professor Schmidt, for the fascinating talk. A slightly off-track question, but are how constant are fundamental constants? This question does bother us. So from your experience with cosmology, are there any answers, or would you be willing to take another bet on it?
Well, that's a really interesting experimental question. So astronomers, including several in Australia, have gone out and they got very excited because they found evidence that alpha, the fine structure constant, was varying back in time. And they did that by looking at atomic transitions and seeing you can calculate how they depend on alpha. And it turned out it was a glitch in a spectrograph that caused the measurement. So we go in and we can measure alpha, we can measure the dielectric constant mu, we can measure, well, those would be the 2. You kind of want to do unitless ones. So you want to do ones that, like alpha, are a ratio. So we can go through and test things like that based on the physical situation. So we're always looking to do that. But at this point, we have never seen any evidence for the physical constants changing. If they did change, they change it's very small, even back, 3/4 of the age of the universe.
Okay, maybe we can end on a lighter note. One of the students asked, what is one of the coolest thing you can tell us about the universe to someone who's not from the physics background?
Wow, I should have had, I'm sure I've come up with something good on that one. Coolest things about the universe, not from a physics background. Well, we've already told you about curvature. We've talked about the Big Bang. I mean, gosh, I don't know. I don't think I have anything up my sleeve that's even better than that. I guess, God, I'm really struggling to come up with something beyond that. I don't know, does anyone in the audience want to volunteer something that's off the top of their head? Say it again. Well, absolutely, but it doesn't exist, right? So the coolest place in the so we'll go for the dad joke. Yes, the dad joke, as we would describe it in Australia. These are the jokes that a physicist's dad would tell at the dinner table around absolute zero. So the coolest thing in the universe is absolute zero, but that's only going to be in a lab here on Earth. The only place you're going to get a temperature like that is inside, a lab. I assume you do Bose-Einstein condensates and stuff, so you can cool things down to essentially absolute zero. In the universe, the temperature is 2.7 degrees right now, and it will eventually, in eternity, get very, very cold. But yeah, I'm sorry, I've completely failed on that last question.
Thank you, Professor Schmidt, for answering all our questions. Let's thank Professor Schmidt. I'll now request Mr. Vinod from the Dean Global Engagement Office to deliver the vote of thanks.
Hello. Let me give you a brief vote of thanks due to time constraint. On behalf of the organizing committee, I would like to express our sincere gratitude to Professor Brian Schmidt, our esteemed guest speaker, for delivering an inspiring lecture. Your valuable insights about our universe have enlightened us, and your presence and words have made a lasting impact on our audience. We would also like to extend our heartfelt thanks to Professor Subra Suresh and Mr. Kris Gopalakrishnan for gracing the occasion with their presence and unwavering support. We must thank Professor Kamakoti Virinathan, Director, for supporting this lecture series. Our appreciation goes to Professor Mahesh Panjagnula, Dean Alumni and Corporate Relations, and Professor Raghunathan Rengaswamy, Dean Office of Global Engagement, for their continuous support and guidance in making this lecture a resounding success. Once again, we extend our sincere appreciation and gratitude to everyone who contributed the success of this lecture. Your support and encouragement have been invaluable, and we look forward to hosting more such enriching events in the future. Thank you everyone.
Thank you, Vinod. I would now request all of you to stand for our national anthem.
Mana Adhinayak Jaya He Bharat Bhagya Vidhata Punjab Sindh Gujarat Maratha Dravida Utkala Vanga Vindhya Himachala Yamuna Ganga Uchala Jaladhi Taranga Tav Shubha Name Jage तव शुभ आशीष मांगे गाहे तव जय गाथा जन गण मंगलदायक जय हे भारत भाग्य विधाता जय हे जय हे जय हे जय 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 हे
Night.